So as I mentioned before, I'm skipping chapter 7, statistics, to do chapter 8, probability, because I think it works better with the other things we've been doing. So we started off with fractions. We moved to decimal fractions. In with the decimal fractions were ratios, proportions, and percents. And probability at its core is a ratio. And often we express that ratio as a percent. So we're just going to explore a few ideas in probability. Probability is a pretty complicated subject, and you can take multiple courses in it at a college. We only offer a partial one here at BMCC in addition to this, but it's wicked cool stuff, and it's involved in our lives all over the place. So we're just gonna jump in and see what we can do with it. So this is chapter 8. Probability. So I just like you to think about two things right now. An example of probability, any example you can think of, maybe directly relevant to your life, and maybe just some idea about probability. And then what does the word probability mean? So before I start throwing out my ideas about it, I just want to get some feedback from you all about what you have in your head about when you hear the word probability, what does it mean and what's an example? So think for a sec, write down an example of a probability situation. And then what does probability mean? I'm just going to write down an example I just thought of. So there's a chance that I will ride my bike tomorrow. We often use the word chance synonymously with probability. All right, so I got one thing, an example in the chat. And if somebody has wrote down an idea they think is interesting, feel free to speak. I'll be quiet for a moment or throw it in the chat also. Hoping you'll all play along with me today and come up with some ideas to share.
How about there's a chance that my teenager will drive me crazy?
Oh, that's a good one, yes. I have a couple of teenagers. There we go. Okay, we have 7 of us here, and so far I have 3 ideas. I'm waiting for 4 more. So if the rest of you could come up with something either on voice or chat, please share. That's a great one. There's a chance my dog might get into the trash. Yes.
Mine too, Bianca.
Well, beg for food. Yeah, there we go. I have a cat who will cry if you don't throw her cat food at her so she can chase it. Write somebody's down. This is fun, isn't it? Come on. Thanks for playing. There's a chance.
Way to be positive, Jimmy.
Yeah, Jimmy, there's a chance I'll get an A on this math exam. Yes. Thank you all. Now we're rolling. Okay, so we had a few different examples here. And when we speak, I think it's more likely we use the word chance, right? That's a more common word than probability. There's a chance that my brother will not do his own laundry. No doubt. Oh my gosh. Trouble. So there's all these things in our life and we're like, man, I hope this happens. And when I hope something happens, it might happen, right? But it might not happen. So sometimes hope is a signal that we're thinking probabilistically. So these ideas of hope and chance and likelihood and probability, they're all the same idea, and they're all a belief, in my opinion. So earlier, let's see, someone wrote, and hey, Adelie, how likely something is to happen. Yeah, so it's a chance something will happen, it's how likely something will happen. And so what we have to do is we have to figure out how to measure these things. In general, I think we can sum up probability in the following way. It's a measurement of our belief that something will or will not happen. So that's the general way we all use the idea of hope, probability, chance, likely. And often when we say likely, I think that's more often it will happen than not happen. Right? So we use some words with a little bit more clarity than others. So chance could be anything. I think most people believe that. So the idea of chance, anything is possible. We use the word likely a lot when we're thinking probabilistically. And most people, I believe, the idea of likely is more often will happen than not. So for example, last year, if you asked me, hey Gary, are you gonna bike tomorrow? I would have definitely said likely. There's more of a chance I will bike than not bike. As far as any of these chance or likely, it's all references to probability. And one thing for sure we can say about probability, because there's much that's very unknown about probability, is that probabilities have to live somewhere between 100%, it's happening or it happened, and 0%, no way that can happen. 100% as a number we learned before is a 1, and 0% is a 0. So probabilities live between 0 and 1. You can't have a probability less than 0. 0 means it cannot, did not, will not happen. 1 means it happened, it will happen with absolute certainty. So that's an important thing to know about probabilities. So then what I'm thinking about likely here, something is likely if the probability of it happening is more than 50%. Right? as a decimal. So that's the way I think about the word likely. And I think most people, when they say the word likely, that's kind of what they're thinking. Okay, so the trick is that we have to come to some terms on is how do we measure this belief about situations? And some are easily measurable and some are not. So just an example of some easily measurable things. I'm going to switch cameras here. Okay, so I threw out a bunch of things here, and so let's simplify the space and look at a coin for a moment. So here I have a dime, and it's got the tail side, and it's got the head side, and I can flip it. I'm flipping it in my hand, just trying to roll it over, and it's a tail that time right there. Maybe you can see that. Then I'm trying to flip it again in the camera's range, but apparently I'm incapable. Another tail, and then I flip it again. Oh my gosh, it's another tail, and I flip it again. Oh, I got a head that time. See that there? So as far as a coin goes, I think there's one option head and another option tail there. You know, maybe it could stand on its edge, but I can't make it do that, so it's unlikely to flip and land that way. So we assume there are only two options. I have a dice here, and my dice has sides 1, 2, 3, 4, 5, and 6. And I roll that, and I get a 2, and I can roll it again and get another 2. Oh, I got a 5 that time. I got a 2 that time. Interesting. Maybe I'm not rolling it very good, am I? I got to really like wind up, shake it in my hand. 4. 4. I'm not shaking it very well, am I? Or I'm just like 2 and 4 day. Okay, there's a 1 that time. So we're familiar with coins, dice, deck of cards. Right? I've got 52 cards here. 2 different colors, 4 different suits. 12 of each. Is that right? 12. Ace through 10. No, 13 of each. I lied. Ace through 10, and then Jack, Queen, King. Other things we use with probability are spinners. We have a spinner activity, and one way to make an at-home spinner is take a paper clip and a pen, put your pen in the middle of that spinner there, and then just flick it. I got a 9. Flick it. I got a 5. Flick it. I got a 5 again. Right? Can you see? I got a 5 there. So a few different things that we're kind of familiar with to simplify the idea of probability. And some of these are used in life often, in games, for example. And then sometimes we like, you know, flip a coin. You get to do the laundry, or do I get to do the laundry today? You have to wash the floor today. Let's flip a coin. Sometimes we might even draw straws. Straws, you've heard of that before. Let's go back to share screen. So some situations are simple enough where we can look at it and we can easily measure the probability. So for example, let's just think about flipping a coin. That's one that's pretty easy to do. So measuring probability. Case number 1, flip a coin. And the options of flipping a coin are we could get a head or we could get a tail. And when you list all the possibilities, that's called your sample space. And so I usually put it in curly brackets, all the possibilities. This is the sample space. And sample space is just a list of possibilities, all possibilities. And we might even say the word outcome is used a lot. Something will happen. What happens? What happens is the outcome. The outcome here is either a head or a tail. And we often believe, so we have some assumptions here, beliefs, assumptions. Assumptions are beliefs. The coin is fair. meaning a head is just as likely as a tail. When you have outcomes that are just as likely as the other, they're called equally likely outcomes. So if these only two outcomes are equally likely, and the best a probability can get is 100%, right? So what's the probability I'll get a head or a tail? Well, I have to get a head or a tail, so that would be 100%. So just note, probability of a head or a tail, those are the only two things that can happen. That would be a probability of 1, which sometimes we'll state as a percent, 100%. Since they're equally likely, right, because this is fair, then that means the probability of a head has to equal the probability of a tail, meaning they have to split this 100%. So that means they must be 50% each, which could be written as a fraction or a decimal or a percent. So with that in mind, I mentioned earlier, I chose to do probability next instead of statistics because probability is all about fractions, ratios. And in general, that measurement comes from taking a look at what we call favorable outcomes, so counting them. Count of favorable outcomes divided by a count of all outcomes. So if I want to get ahead, then there's only one way to get ahead. There's one head, right? So there's 1 for my numerator. And then how many outcomes are there total? Well, a head or a tail, there's 2. So here's my 1 over 2 for that. And we can make the same thing happen for a 6-sided dice. So that's another example that's easily measurable. So 2, welcome Julian and Montse. Dice. Most common type of dice we see is 6-sided, but there are many other types, 4-sided, 8-sided, 10-sided, 12-sided, 20-sided. I used to have a 100-sided one. That one was cool. Somebody borrowed it and never gave it back. I haven't found a new one. So a 6-sided dice. So the sample space for a 6-sided dice is typically, but not always, there are different kinds of 6-sided dice out there. It's usually a 1 and a 2 and a 3 and a 4 and a 5 and a 6. And like I showed, the one I had in my hand a minute ago, they have pips on them. There's little dots, right? So there's either 1 pip or 2 pips or 3 pips or 4 pips. Don't ask me where the name pip comes from. I've just heard them called that before. So if I wanted to know what's the probability of rolling a 3, we usually abbreviate that with P for probability, parentheses 3, and hopefully in the context we realize that it's a 3 on a 6-sided dice. Well, there's only 1 3 on the dice I just showed, and there were 6 possible numbers, so it should be 1/6. Now, since 6 isn't just a 2 or a 5 in the denominator, when I try to change it to a decimal, it gets a little messy. 0.16 and the 6 repeats. So that's kind of a pain. So I might approximate it and say it's 0.167, or as a percentage, 16.7%. So a fraction, if we can write down all the possible outcomes, we can exactly state a fraction for the probability. A percent sometimes is an approximation if the fraction doesn't make a nice decimal, and it doesn't this time. Now, not all probabilities are that simple, even though they sound that simple. So I'm going to put up another situation here that's simple, but not. Oops, if I could spell my name right. Gary throws free throws. Okay, so Gary throws free throws. Now, either he gets it in or out. So as far as outcomes go, right, my sample space, what can happen? Either I get it in or I don't. So we could say they're called in and out. And I'm going to change the camera again, and I'm actually going to throw some free throws. Let's see, we got it. Stop sharing. There's me. Let me see myself. There I am. Okay, so I'm going to set up. There's my chair over there. Here is my basket. My trash. Let's see, we got that there. And then for a ball today, I have my lovely orange snack here. And so I'm going to throw some free throws in there. Ready? What's the chance? Ready? Oh my, I missed. Ooh. Okay, I'll get it this time, right? Because it's either in or out. So if I missed the first time, I got to get it the second, right? Isn't that the way it works? Oh my gosh, this is sad. Okay, what's the probability Gary gets a free throw? How about 0 based on this evidence? Ah, I got one. Okay.
Yeah.
Thank you so much for the enthusiasm. So based on that evidence right there, right, Gary has a 1 in 3 shot of getting a free throw. That's kind of sad, but true. I'm better with a soccer ball. Let's go back to share screen. So sometimes when we look at a situation, we might assume things are equally likely, but they're really not. And how do we really know? Now, it's usually a belief. That coin I was flipping, I got an awful lot of tails before I finally got a head. So in this case over here, these aren't equally likely. And you might say, well, he was just nervous because he was on camera, and let's give him a real basketball at a basketball court. Well, if they were equally likely there, then me and any NBA player, put us together, we get the same chance of getting it in. I might as well play in the NBA. I'm pretty fast, agile. I don't think so. So this is a lot more complicated situation than the coin, which had 2 outcomes. We had a belief with the coin they were equally likely, but in this case, did I clearly show they're not equally likely? No, I only did 3 tries. You could flip a coin and get 3 heads in a row, right? That happens. So what happens and the probability of an event are 2 different but related things. And we'll get to how they're related in a little bit. So this isn't like the coin situation where I can just look at the situation and say, oh, these are the probabilities. The only way to know this one is through experiment. So these probabilities can only be found through experimentation. So we just have to watch it happen over and over and over. We have to just keep repeating this experiment. And every time we repeat the experiment, it's a trial. So then I would end up with this table, this spreadsheet. So I would have a result and I would have a trial. So for example, a moment ago in my first trial that we observed, let's say a 0 is not in. So that's an out, 0, and a 1 would be in. So trial 1 was a 0, trial 2 is a 0, trial 3, I finally got it in. And let's suppose I'm fairly consistent, and so trial 4, I'm going to miss it. Trial 5, let's say I missed it. Trial 6, I'm getting nervous, I'm going to miss it again. Finally in trial 7, I get it in. I'm on a roll though, trial 8, I get it in, right? We just have to watch it happen. Right? If I only did 8 trials and these were them, then the best you could say is the probability that Gary gets it in, based on just those 8 trials, would be there are 1, 2, 3 ins out of 8 total trials. So Gary has a 3/8 chance of shooting a free throw and getting it in. On the other hand, as far as it not being in, it's out, right? There's 1, 2, 3, 4, 5 ways that can happen. And this always has to be true. The total probabilities of the individual events, they have to add up to 1. So often these are called simple events because there's only one way it can happen. So sum of simple events is always 1. There's only 2 simple events here, the probability of in plus the probability of out is 3/8 plus 5/8, which is 8/8, or 1 or 100%, right? Something happened. These are only 2 things that can happen. So what's the probability that something happens? Hey, it's 100%. What's the probability nothing happens? Well, that's 0%. Something always happens. Remember, probabilities have to be 0. Anything up to 1 can't be bigger than 1, can't be smaller than 1. This idea of simple event, I mentioned it, but I didn't write it down. Let's make that clear. A simple event cannot be broken down into other simpler events, other smaller events. Cannot be broken down into other events. So as far as the free throw thing, there's only 2 events, in or out. It's not that complicated. So let's look at something that's a little more complicated. Let's go back to the dice. So I have a 6-sided, and the singular is die, plural is dice. So I have a 6-sided die, right? This QB thing, and the QB thing has numbers on it, like a 1, and a 3, and a 5. So here's my rendition of a dice, and we're going to roll it. And so there's lots of things I can ask. Like a minute ago, I asked, hey, what's the probability of getting a 3? Well, that's a 1 out of 6. What's the probability of getting a 4? That's also 1 out of 6. But we could have more complicated events than just getting a 4. Like I could say, hey, what's the probability of getting an even number? All right, well, what does it mean to be an even number in this case? Well, there's a 2 on there, or I could have gotten a 4, or I could get a 6. So there's 3 different even numbers I could get. So the probability of rolling an even number is 3 out of 6, or 1/2, or 50%, or 0.5, right? Lots of ways we can write it. With probabilities, I sometimes don't bother reducing them. Like this isn't okay to state an answer for a probability because it shows me, hey, there were 3 favorable outcomes, there were 6 total outcomes. And then sometimes I'll just go straight from that maybe to the decimal or percent version. So it's okay, in my opinion, to not reduce probabilities sometimes because, again, they show us favorable outcomes and total outcomes. Other thing I could ask is, what's the probability of getting a prime number? Let you guys think about that for a minute. See if you can come up with a number for me. What is the probability on a 6-sided dice of rolling a prime number? And there's all kinds of online dice roller apps. There's one like random.org that I like. Google used to have one. Why didn't it pop up? Roll dice. There we go. Thank you, Google. Hey, I got a 6. Isn't that cute? Rolls it around. Whoa, making me dizzy. I got another 6. What the heck? Hey, I got a 5. All right, anybody got a number for probability of a prime number? 3 out of 6 says Monsi. Okay, let's see. I'm gonna put down the sample space just to be clear. I think that is correct. Sample space is a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And in this case, I could list the favorable outcomes by identifying which of those are prime. 1's not, but 2 is. Or 3 is prime. Or 4 is not, 5 is, 6 is not, 5, and Moxie is correct. It is 3 out of 6, or 50%. So there's a 50% chance of rolling a prime number. Hey, there's a 50% chance of rolling an even number. Is this true? Question mark. What's the probability of rolling an even number or a prime number? Since they both are 50%, is that, question mark, 100%? Seems like that might be possible. What do you think? Prime or even? Let's see. Is there any number that's not prime, not even? I think I see a flaw here. Anybody else? I don't think it's 100%.
So it has to be even or prime, but it can't be even and prime, like number 2?
Ah, good question. So in math, or is in, and I talked about this way back in 211, it's been a while, or is an inclusive idea. So in regular language, or is exclusive. So like if I say, hey, you can have cake or ice cream, the implication is I could have cake, I could have ice cream, but I can't have both. In math, the or is inclusive, which means one, the other, or both. So sometimes a mathematical or in regular language could be written as and/or. So you could have ice cream and or you could have cake. Oh, cool, I could have both. I want both. So in this case, prime or even is any of the number that's even, any number that's prime, but it could be both. So if I list those out, the even numbers were 2, 4, and 6. Now I'm not going to list 2 again because I already wrote it down. So then I would write 3 down and 5 down. Oops, that's not 5. So these are all of the numbers that are even or prime. 2 happens to be both. There are 5 of those numbers, so the probability of being even or prime is 5 out of 6, which is not 100%. So we do have to be careful when we combine events if they're not simple. If they have any kind of overlap, like we have here, then we run the risk of double counting when we throw them together with an or. So an important rule in probability that gets to that, and we looked at this rule way back in set theory, so I'm going to bring up some set theory stuff here from the first quarter. Remember set theory where we drew these Venn diagrams? So this is my sample space here. And in my sample space, I had this event called even, and I had this other event called prime. Come on, Gary, draw it better. That's a little better. And this one was called prime. And my universe here is just the numbers on a 6-sided dice. So 2 is both even and prime, it has to go there. 4 is even, but not prime. 3 is prime, but not even. What else do I have? 5 is prime. 6 is even, but not prime. And then there's 1, which lives out here. It's neither even nor prime. So it goes outside the box here. So Venn diagrams can be helpful in doing probabilities. So the probability of being even, I'm going to use even and prime. 2 is the only number that fits that description. So that probability is 1 out of 6. The probability of just being even, we looked at earlier, that is 3 out of 6. The probability of being prime is also 3 out of 6. And these 3 events go together to form the probability of being even or prime. So that would be the probability of being even plus the probability of being prime. The problem with just writing this right here is they both counted the 2. So then we have to say, okay, let's remove that double count by saying remove what they have in common. Even and prime. And this idea is true in general. So in this case, I get 3/6 plus 3/6 minus 1/6 gives me the 5/6 that I found a slightly different way. And this is a general rule for probability. For any events, let's just call them event A and event B, and think about the Venn diagram. So if we use a Venn diagram to think about this, here's event A, here's event B. They may or may not have an intersection. This could be empty here. But in general, the probability of A or B happening is equal to the probability of A happening plus the probability of B happening minus the probability that they both happen, A and B. Remember before we talked about the or, that's a union in set theory, and the and is what we talked about way back, it's an intersection. So those ideas of set theory that we looked at long ago are super helpful for probability. Other things that are important related to set theory and probability, a complementary set. So we might have some events, and I'm just going to call it A. It could be, for example, even. Then there's the complement of A. Which is everything that's not in event A. Right, so not even. Venn diagram wise, if this is event A in here, then the complement of A lives outside of there. Maybe use a different color for that. And there's lots of different ways to do a complement. Usually I put a bar over it. So the complement of A would be A with a bar over it. Everything that's not A. So sometimes you just call it not A. Sometimes you'll see that, not A. So that's everything outside of it. And together they represent everything in our sample space. So the probability of A happening and the probability of not A not happening, that always has to be 100% or a 1. And so this gives us kind of a cool relationship that the probability of A not happening is equal to 1 minus the probability of A happening, or vice versa. Probability of A is equal to 1 minus the probability A doesn't happen. Right, so this is a nice relationship between complementary events. And we do have to be a little bit careful about complementary. In this case, like if I was talking about the dice example again, and A was my even 2, 4, 6, then not even numbers are 1, 3, and 5. And in this case, we have a word for not even. So that works okay. But we don't always have a word for not something. A simple example when we don't have a word for not something is, let's think about the dice again. And suppose we look at prime numbers. And so in here I have my primes, which are 2, 3, and 5. And so let's suppose that's my event A. So A is being a prime number. What is not A? Well, not A is just not prime. Do we have a name for not prime? What do you think? Like not even is odd. Did we ever come up with a word for not prime? Silence. Okay. One thing people often say here is composite. The problem with composite means it has multiple factors composed of many things, but there's also one. The number one is not prime and not composite. My point here is just we often have to think hard about what we're doing and don't take anything for granted. Sometimes there is a simpler way to say not something, but often there is not. It's just everything outside of that. Okay? All right, let's see, what else should we look at here? Let's do an experiment. So we're going to take a little break. There's a ton of rules to go over, and I've gone over about half of the rules so far. I got a few more to go over. I want to take a break from rules and play a game. So let's take a look at the activity, and then we got to figure out how we're going to do the activity. So basic probability activity here. This one I made a discussion because I want each, and we're going to do it in groups, I want each group to see the results of the other groups. Blow that up a little bit. So we're going to explore probability through a game, and I wanted to do something a little different than flipping a coin or rolling dice, and so I thought a spinner would be fun, and this is one usually people can do at home. Now the problem with doing this at home is you have to have a nicely drawn spinner, and if it's too sloppy, then it could throw things off. So here's what I mean by that. So here's my spinner 1, 5, and 9 on there. And I'm just going to redraw that. So say I'm working from home here, and I'm going to do my spinner. And so on my piece of paper, and you guys know how good a drawer I am with this magic pen. Sometimes good, sometimes bad. Ooh, that's a pretty good circle. And then I have to split it into 3 sections. And so I do this right here. Okay, so there's my 1, 5, and 9. Is that good enough to replicate this? If not, how are they different? I'm going to draw another example. Let's suppose Gary's brother, who's not as good a drawer as Gary, gets in here, and he does this, 1, 5, and 9 for his 3. What do you think about these spinners compared to the one I computer generated?
They're not going to work because you're going to be more likely to get a 9 in the one of them because it's bigger, and then the one on the other one is a lot smaller, so that they're just not equal probabilities.
Yeah, so this one for sure is a problem. If this is where my spinner starts and then flicks around, 9 is going to happen like half the time, and the 1 and the 5 are going to happen maybe a quarter of the time if those are right angles right there. With this one right here, this would be okay if this angle is the same as that angle is the same as that angle. And I did actually try to make those angles the same, even though I was a little sloppy about it. So I'm just going to grab a screenshot of my other one here. A nice clean one. So this one I had a computer draw it, and when I told the computer to draw it, current please, I said, okay, there's 360 degrees when I spin around a circle, and so I said, okay, let's take 360 and divide it by 3, so that means each of these angles should be 120 degrees, 120 degrees, 120 degrees, because the degrees are what the spinny thing is covering, right? Every time it goes around, it covered 360 degrees. So as long as all of those angles are the same, 120 degrees each, then this is a good, fair spinner. So one problem with us doing this at home is if you don't have a printer to print this out on, then you may not have a fair spinner, and it could put you at an advantage or a disadvantage that we didn't mean to happen. Okay, so how do we cope with that? Well, we could pray everybody's a good drawer and can draw a 120-degree angle properly, and some days I'm good at that and some days I'm not. And I don't have a printer at home anymore, so if you ask me to print this, I'm like, oh, I could hold a piece of paper up to my screen and I could try and trace it, right? That's the best printer I could do at home right now. So some other ideas I came up with is I made a spreadsheet here, and spreadsheets have random number generators. And so I tried to use, let me blow this up a little bit. I tried to use the spreadsheet's random number generator to fairly choose a 1, a 5, or a 9, and you would hit F4 to spin. So every time I hit F4 on the keyboard, oh, come on, don't lie, it worked at home. F4. Ah, it doesn't work here. Maybe it's Shift F4. Control F4. Oh, man, that deleted it. No, where'd it go? It worked on my home computer. Now I'm failing. F4? No. Huh. If somebody could do me a favor, bring up this spreadsheet, which is linked where? Over here. When I was at home, F4 made it work. Okay, so maybe on other computers it's a different. Okay, so I tried Control F4. That was a problem. Oh, whoa, somebody else is making it work. Cool. Okay, is that me? No, I bet someone else is in there. Usually it shows me if other people are in here. Huh. Alt F4? Oh, Shift F4. Oh, what did I do? I'm just totally messing up my computer. Oh, not that one. Oh, that closed my whole browser window. All right, so I am totally failing at this today. I swear I tested this earlier. Well, apparently that's not going to work because the keystroke that I used earlier on my home computer does not work on my office computer, which means it might not work on your computer. Okay, so I got another idea in case that failed. Trying to come up with as many different ideas as we can to make this succeed. Another way I know I can make it work here. Oh, we have someone else there playing with it. Oh, somebody else is making it work. Are you hitting F4 there when you do that? Or is it just new people looking at this that's making it change?
I tried it and it didn't work. But...
F4 didn't work for you. So one thing I know that will work is if I go into a different cell and I type anything and hit enter, it will regenerate the random numbers there. Every time I do it, it'll re-roll. Most spreadsheets have Excel. I thought had this. What if I download this to Excel? But not everyone's going to have Excel. So anyway, I'm trying to find a way to fairly spin for each of us so we can play this game together. So if I download this, reopen it in Excel, maybe the F4 works in Excel. Enable editing. Blow it up a little. All right, and I'll show you my other, I have two other ideas just in case. So here, if I hit F4, it doesn't work here either. Man, I thought that was it. F1, no, 2, ooh, really not that. 3, 4, 5, no. Shift F4, no. Control F4, no. Okay, well, I bungled that up. All right, let's go back and okay, so one idea that for sure does work here, yeah, you can go away, don't save, is every time we type something, it will shift it. So you could make your own copy of this by going make a copy or download it. And then you could pick your spinner, your neighbor's gonna pick their spinner, and every time you change what's in, say, this cell over here, that'll re-roll the dice. And how I made that happen, I'll talk about next class. You could look at the spreadsheet if you want to figure that out, but I'll talk about it next time. All right, so that's one option. Another option is to actually just roll a real dice. So let's go back to random dice. And maybe I use the random.org one, or maybe I use the Google one. I'm just going to roll one dice. And then since there's 6 numbers on the dice, what I could say is that If I get a 1 or a 2, that's my first number. If I get a 3 or a 4, that's my second number. If I get a 5 or a 6, that means pick my third number. So whichever spinner you have. So if I rolled a 2, I would get a 3. If I rolled a 3 or a 4, I would say it's a 4. If I rolled a 5 or a 6, it would be an 8. So that could work. Third option is this random number generator here. And what I told the random number generator here to do was to pick a number 1, 2, or 3. And then I said, give me 40 of them. And so this, for example, could be all the spins of the first column could be player 1, and the second column could be player 2. And this is your third number, second number, first number, second number, and so on. So if I had if I rolled a 2 here, that would mean back here, I got my second number, which would be a 6 if I was on B. So some way we have to find a way to do randomness for ourselves. I'm going to split you into teams. And what I want you to do is I want you to each make your own table. Your table is going to show which trial you're on, what spinner you have. So you're going to say my spinner's B or my spinner's C, what your partner had, what you rolled, what you spun, what your partner spun, whether you won or lost. So eventually you're going to make a table. And again, the table will have which trial you're on, and you're going to do this at least 20 times. So 1, 2, 3, 4, and so on. Whatever spinner you have, maybe I pick spinner B, and maybe my partner picks spinner A, and then my win or loss. So maybe I had spinner B and I got a 2, my partner got a 5 on theirs, so I have a loss. And then I just keep doing that over and over. This time I spun a 7, my partner got a 5 again, this time I won. And what we want to do is we want to use this data here to then answer some questions. And the questions we're going to answer are, we're going to make a guess first. Guess whether your spinner might win more often than your partner's spinner. But first we got to split into groups and pick spinners. And you can't have the same spinner. So you guys got to figure out how to equitably make that happen. And then for your spinner, like if I said I was picking spinner B, so 2, 6, and 7, based on my 20 spins, what's the probability of getting a 2? What's the probability of getting a 6? What's the probability of getting a 7? And then what's the probability I won against my partner? And I would just look at the 20 things and just count how many times I won. And that's what you'll submit. And I want this in everybody to see everybody else's results, because we're going to pool them all together when we're done, either today or next class, and look at the group data. And what we're doing here is we're comparing what's called theoretical probability to experimental probability. So a quick note on that, and then we'll do this. So theoretical probability . Theoretical probability means we know everything there is to know about the situation. And because we know everything, we can state probabilities exactly. Like, I believe I know everything there is about flipping a coin. It's either a head or a tail. Probability is 1/2 for a head, right? I think I know that exactly. Same thing with a dice, same thing with a deck of cards, same thing with a spinner. That's theoretical. Experimental is we run multiple trials of an experiment. And the experiment has to be repeated the same exact way each time. So like flicking a spinner, flipping a coin, rolling a die. me shooting free throws. And then we calculate probabilities by looking at the favorable outcomes divided by total outcomes. So favorable divided by total. And the difference is the probabilities in experimental come from only the observations we made. So like when I was throwing the free throw, I only threw it 3 times. So the probability of me getting it in was 1 out of 3 based on those experiments. If I did more experiments, it might change. And experimental and theoretical probabilities are related to each other, which is what we're trying to get an understanding of. So this experiment we're doing right here is about experimental probabilities, and then we're going to turn them into theoretical probabilities and do a comparison of them. And the more data we have, the better off we are. So I'm going to split you guys into groups. And let's see, as far there, do we have an even number? All right, so one person is going to have to play with me. And let's see, that looks good, that looks good, that looks good. So I am going to pick, I need another add a room. Okay. So I've made the rooms. So again, what's going to happen once we go into our rooms is you and your partner have to decide 2 things. How are you going to go about your spinning? Did you print this? Are you going to draw it and try to use a paperclip like me? Are you going to try and use the spreadsheet to do it? Or are you going to use dice or the random number generator to do it? If you're not sure about any of those options, then let me know and I'll help you figure it out. But talk it over with your partner and then grab me if you have a question about how to make this happen. Once you figure out a way to fairly generate these 1, 5, or 9, or 2, 6, or 7, or 3, 4, and 8, and again, we have to, you and your partner have to agree that whatever method each of you chooses, that you're just as likely to get a 3 or a 4 or an 8. Right? We have to believe that each has an equally likely outcome. Otherwise, this experiment won't work quite right. And then we have to do at least 20 trials, record it in a table, and then we'll see where we are. Questions before we head out? Okay, so.
Well, really quick, I must have missed something. So we have to draw this table? That's what you're saying? You're
going to either have to draw the table or whip out a spreadsheet. Yeah.
Okay. Thank you.
One or the other. The easiest thing to do is draw it. Okay, let's go.